Okay, so far we have finished, we have achieved all three goals that we set out to achieve. Yeah, the first goal was to show that every single monomial algebra, every single finite dimensional algebra is, studying its representation theory is essentially like studying the representation theory of bound quivers. Well, I was looking for some material yesterday and then I found this interesting quote. Yeah. So from Michael Barrett from UNAM, Mexico. So, as it seems, all what we have to understand in order to study finite dimensional modules over finite dimensional algebras are representations of quivers. However, we should warn here that this could be misleading, since in many cases the quiver of some interesting algebra is wild, whereas the algebra itself is tame. Well, I don't really understand this. Finally, it should also be mentioned that we really lose information by the reduction to indecomposables and the morphisms between them, as the following example shows. And then he explains the, the following example in this case is actually the example of a single point, single vertex, no quiver, no arrow quiver. Yeah, just A1. The study of representation theory of A1, yeah, is the study of finite dimensional vector spaces and linear maps between them, which is what we normally call linear algebra. However, there is just one indecomposable, and morphisms are just multiples of the identity. The Auslander-Eiten quiver of A1 is again just a point, and this is a terribly reduced view of the whole linear algebra. So linear algebra is meant to be more interesting. However, following this path, we might lose lot of information. Yeah, so that I think Upendra already made this point earlier when we saw that the matrix ring, the matrix algebra is Morita equivalent to the field itself. Yeah, so at that time he said that, yeah, the dimension vectors of finite dimensional modules over the matrix algebra, they still matter. But by following this method, we are doing the opposite. Actually, there is another quote which I want to read out from the same person, and that is about the usefulness of Auslander-Eiten theory. So if you do not see Auslander-Eiten theory and you only know the basic tools, yeah, you start with AN, DN, then E6, E7, E8, and then maybe you try to work out the example of Kronecker. So what happens? Well, please listen to this quote. Classifying is one of the most important problems in representation theory, but clearly there are many others. We used only linear algebra, which is simple and powerful enough to do the job. However, you should have noticed that we lack some general strategy. Yeah, so furthermore, we gained no structural insight and got just a plain list of indecomposables. There are methods, better methods, very effective when applied to examples because they are somehow self-correcting, which means that mistakes tend to surface quickly. These better methods are based on the Auslander-Eiten theory. So basically, like if you know one indecomposable and you know how to compute the Auslander-Eiten translate, for example, then you can fill up that component, that connected component. So you'll have a better idea of the Auslander-Eiten sequences as well as the translates. So how different things, the morphisms, how morphisms work as well. So a lot of information is actually captured by the Auslander-Eiten quiver. Okay, so these are like, Michael Barrett calls them self-correcting methods. I just wanted to point these things out. And yesterday we ended with one application of this particular corollary of existence of Auslander-Rayton sequence. Yeah, we said that under certain conditions, any non-split extension is almost split, which means that under certain conditions, if you know something which sits in the middle, like even if you know something which is indecomposable and sits in the middle, then we can conclude that this sequence is non-split. So very interesting result we saw here. And we looked at one example as well. And however, I also want to connect this back with what Upendra was doing for a week. Yeah, the proof of Gabriel's theorem, the study of reflection functors and Coxeter groups, that was crucial. So even there are more general Coxeter methods. So Coxeter transformations. This is a short topic I want to cover, and then I will try to do something else. So here we have to assume that the global dimension of A is finite. Yeah. We have to make this blanket assumption, otherwise the methods here won't work, and you will very soon see what I'm talking about. So you can define the Cartan matrix CA associated with A, whose ijth entry is the dimension of the vector space EJAEI. And you can notice very easily that the ith column is the dimension vector of the projective, whereas the ith row is the dimension vector of the injective. Okay. So the determinant of this matrix is actually either +1 or -1, which means this matrix is invertible. So let us look at the proof. So we have to start with some projective resolution of SI. But I'm not just looking at the resolution, I'm also looking at SI. So this is an exact sequence, but because the global dimension is finite, yeah, which is what we need for completing this proof, that because the global dimension is finite, you have this finite length projective resolution, and where each pi is projective, and then because the dimension vectors just add, like the total dimension vector of this sequence, that is 0. So the alternating sum of the dimension vectors is 0. That is what I wanted to say. Sorry. So the dimension vector of the simple module, which is just 1 in ith place and 0 everywhere else, the standard basis vector. So this can be written as the dimensions of this sum of dimensions of PJs. Okay. So the alternating sum of dimensions of PJs. Now every module, every single projective module is a finite direct sum of these projectives. And therefore, simple linear algebra tells us that this right-hand side, yeah, we can write in terms of this sum vectors in z to the power n. We had to take one copy of each, certain number of copies of each projective module to get this particular PM. Yeah, we encode that data in the form of how many copies of projective module Pi in the form of this vector, which is a vector in z to the power n. So what do we get? That dimension vector of Si is Ca times the column vector Di. Okay. And once we know this, then we can combine all these Di's in the form of a single matrix, which we call as D, and then combining the standard basis vectors on the left-hand side, we have obtained the identity matrix. So this shows we actually constructed the inverse for the Cartan matrix. This Cartan matrix will, of course, agree with what Upendra did. Yeah, the matrix obtained by through a series of no, sorry, not the Cartan matrix, perhaps. Yeah, the Coxeter transformation. So it is simply defined to be minus Ca transpose Ca inverse, which is an automorphism of Z to the power number of vertices. Automorphism means it's a linear map as well as invertible. Okay, so this Coxeter transformation will agree with the sequence of uh, those reflection functors. It was obtained, yeah, for a particular admissible sequence of reflection functors. The composition will be this precisely this Coxeter transformation. So we are generalizing that kind of technique for finite global dimension algebras. And here is a simple observation that if you apply this Coxeter transformation on the dimension vector of Pi, the projective module, then you get the negative of the dimension vector of the corresponding injective module, which is nothing but new Pi. Yeah, if you remember our Nakayama transformation. Okay, so let us look at this. So dimension vector of Pi is Ca times dimension vector of Si. Yeah, this is just uh, some standard calculation, and then you apply phi a on this negative phi a, and then this Ca inverse and Ca will cancel, and you will get the dimension vector of II. And this actually helps us with computing the dimension vector of the Auslander write and translate. So even if we don't know what it is, yeah, we can calculate the dimension vector and then look for all the indecomposables and see if something fits in the mid in that position. So this is a useful tool to have. So given a minimal projective presentation, we can calculate the dimension vector of the translate tau m as phi dimension m minus phi dimension kernel m plus dimension of nu m. Okay. So the proofs are actually, the proof is quite simple. You complete this exact sequence. P1, P0, M were given. You take kernel M as well. And this is the second sequence, which is the injective resolution of tau M, nu P1, nu P0. And then you complete it to nu M0. This is the co-kernel of this. And then you simply compute the dimension vectors. So dimension vector of P1 minus dimension vector of P0 is dimension vector of kernel minus dimension vector of M, then apply phi A, and recall this result which we wrote at the top, that minus dimension of minus phi A of dimension Pi is dimension of the corresponding new Pi. So we have this, and then you do the computations and you'll get the result. So we have some way of computing the dimension vector of the Auslander write and translate by knowing by just knowing what this Coxeter transformation is. Any questions or comments about this? Okay. So then let us start talking about the second classification problem. Let me quickly recall. The first classification problem asked, if given a finite dimensional algebra, you can classify all finite dimensional indecomposable modules and the irreducible morphisms between them. That was our classification problem 1. And the second classification problem is, depending on the complexity of the first classification problem, classify the algebras themselves into 3 types. Well, we don't have to talk about all algebras over here. let us just talk about these three Kronecker quivers. So Kronecker 1, Kronecker 2, and Kronecker 3. With like n Kronecker is with n arrows in between. A quick history about this. So basically, the first one is talking about classification of a matrix. Yeah, I mean, you can always assume that the map corresponding to this alpha over here in the representation is injective, or you replace it with the inclusion of the image into the target. And over there, you can see that they are classifying the isomorphism classes of matrices, sorry, the conjugacy classes of matrices. The classification problem for K2 is nothing but classifying two matrices up to simultaneous, pairs of matrices up to simultaneous conjugacy. And then the third one is, no, maybe I'm not saying it right. No, that is a different problem. Yeah, this is not exactly that. I'm sorry. Yeah, that has to do with one vertex in the middle and then all incoming arrows. If there are n incoming arrows, then you talk about the n subspace problem. Yeah, here we are talking about something different, but these are three Kronecker quivers. And the first one is, of course, we know its other name, that is A2. So this is type A quiver. So it is a finite representation type algebra. Then the second one is K2. We computed this 2 days ago, computed the Auslander-Eiten quiver for this in the tutorial. And this is a tame representation type algebra. I will describe what these mean, tame and wild. And the third one, however, is a wild representation type algebra. So loosely speaking, we have said that tame means we have some control over the situation, whereas wild means we have lost hope. Yeah, we don't have any control over the situation, like the classification problem. Well, so what were the naive definitions of wild representation types? So say that an algebra is representation wild. That's another terminology for this. If its representation theory contains the representation theory of every finite dimensional algebra. Yeah, that is how it is defined very loosely. And the second one that we had already written was that an algebra is representation wild if its representation theory contains the representation theory of K3. The path algebra over the Kronecker 3, 3 Kronecker algebra. Now, why is this particular 3 Kronecker algebra so special? We wanted to claim, like attempt 1 is what? That it contains representation theory of all finite dimensional algebras. Well, first of all, we have to make precise the idea of containing representation theory of some other algebra. And that is the definition of a representation embedding. And here I want you to notice that we are not considering finite dimensional algebras necessarily. Yeah? So given any two K algebras A and B, a representation embedding is a functor from the full module category to the full module category, like over A and over B, which is K-linear. So it preserves linearity, scalar addition and scalar multiples, then exact. So which means it takes short exact sequences to short exact sequences. Then conservative. Yep, conservative means it reflects isomorphisms. So functor is said to be conservative if you map it to something like you take a morphism G in category A mod and capital F of G is an isomorphism, implied G is an isomorphism. Okay, so that is the definition of a conservative functor. And that preserves arbitrary direct sums, not just finite, then direct limits and indecomposability. Yeah, this looks like we are demanding too much, but there are nice descriptions for this representation embeddings. The functor, they are actually tensor functors. I'll show you something very soon. But yeah, I mean, in terms of this attempt to, if we want to take this as our definition, that K3 is bad. Yeah, if that's our definition, then first we have to understand why is K3 bad? Why is this particular algebra wild? So let us try to do that. I'm going to draw one particular so just hold on a minute. I think that's so K square and K. I have three arrows. So I need to draw one representation, which means I need to describe three different arrows, three different linear transformations from K square to K. The first one is the first projection. The second one is the second projection. However, the last one that we are taking is any arbitrary pair of scalars. So what we do, if xy is a pair in K square, then lambda x plus mu y. Okay. So this is our transfer representation. And notice that there are two different parameters in this system, in this representation. The dimension vector of all these representations is the same. It is 2, 1. However, what we are, focusing on is that there is a two-parameter system. Well, let us try to understand what happens if we have another transformation, which is in the same family. So this is 1, 0, then 0, 1, and the third one is lambda dash mu dash. Maybe some other pair of morphisms. Then I try to take one morphism here. So let me call this, let's say, what is a good scalar? Let's say eta. And here I'm going to take ABCD, some matrix. And we can try to solve for these matrices so that it is an isomorphism. Well, the first one says that like this top arrow 1, 0 and 1, 0, that tells you yeah. Well, you try to do this, and this is an isomorphism. So ABCD eta, this pair is an iso if and only if you can conclude that lambda is equal to lambda dash and mu is equal to mu dash. So actually, there is a genuine two-parameter family of representations just in a very small dimension vector. And this is the main reason why it is wide.
Are these indecomposables?
Yes. They are also indecomposable.
Two-parameter representations will always get.
Uh-huh.
The point is that these are indecomposable, right?
These are indecomposable. Yeah. These are indecomposable because we are writing K square to K. Yeah, right. Both notice something here that the any two maps are linearly independent. I mean, unless lambda and mu have very specific values. Yeah, so they span what should I say here? Yeah, any two maps are linearly independent. So any questions like why two parameter family is bad? I mean, maybe you are always used to working with two parameter families, and therefore you don't find this problematic. Yeah, there is a group of representation theorists who think that this is not, like, not all hope is lost. However, yeah, I mean, for a simple-minded person, this problem is too complex. And the reason behind that is actually this. Yeah. So let's solve A, denote the statement that there is a satisfactory solution to classification problem 1 for algebra A. Satisfactory. Yeah, I mean, if you do not agree that K3 is wild, then yeah, that's your choice. No problem. But if you agree that K3 is wild, then yeah, that it's not a satisfactory solution. And what we can show actually, that if you can solve the classification problem 1 for K3, then you can solve it for every finite dimensional algebra. But notice something interesting. When we say every finite dimensional algebra, then that means the right hand side also implies the left hand side. Which means, yeah, let me rephrase that in terms of representation embeddings. A wild representation algebra, maybe, yeah, I should write it. So, IE, not sure where my pen is. Yeah, okay. So, IE for any representation wild algebra A, yeah, there are representation embeddings from A mod to K3 mod and in the opposite direction. So they are all equally bad. If you agree that they are bad, then they are all equally bad. Yeah, so this is what we are going to show now. That if you can solve the classification problem for K3, then you can solve it for any algebra. And we will do it in steps. So the first step is solve K3, solve KK3, implies solve KL2. Yeah, where L2 is this loop quiver with only one vertex and two arrows, two loops. So this is our first goal. How do we do something like this? Yeah, from one loop to another. Well, no, sorry. So we have to define, we have to start with rep k KL2, and then we have to describe a functor into rep k KK3. Okay. So what do we do? Idea is very simple. You have one representation, which is V, with a pair of endomorphisms. Let me call them phi1 and phi2. Where do you map it? Any guesses? If we are given one vector space and two endomorphisms, where do we map it to? for KK3. The idea lies in this diagram. Yeah, why KK3 is wild. Okay, maybe I will help you. I need, for giving a representation of K3, I need two vector spaces. I actually follow the same pattern. Yeah, I take V direct sum V and
V
I take
square
V.
to V, then phi 1 0, 0 phi 2, and mu phi 1 plus.
No. 51005 we won't do that. We actually
Oh,
just do the block projections. We just take the first projection, the second projection. We don't change this. The third one, however, we will introduce 5152. Yeah. So very clever idea. And like it shows you how delicately the structure of the quiver matters. Okay, so then the next thing is, of course, I mean, we have to define a functor. So maybe there is some W with psi1, psi2, and there is a map, linear map from V to W. Then what do we do over here? We have W direct sum W and W over here. The same thing over here is 1, 0, 0, 1, and psi1, psi2. Well, you can check that the direct sum of F with itself, which is this diagonal matrix, together with just taking an F here, this will be a map of representations. So which means we have functorially mapped it. Now this is a simple enough check to see that this is actually a linear functor, this is exact functor. Then if you are just solving it for finite dimensionals, then you have to argue that it preserves indecomposability by computing the endomorphism rings. This is local implies this is local. Okay. So this means if we can solve it for K3, then we can solve it for K2. Yeah. Okay, so step 2. So loop quivers are also bad. Loop quiver L2 is bad. But more generally, if we can solve it for L2, then we can solve it for LT. Where LT is again a loop quiver with T many loops. And so now this is literally based on common sense. Yeah? Nothing deep is happening here. So let us take rep K, KLT. We have some representation of LT and we want to map it to a representation of L2. So what do we have here? I have a one vector space and I have T many maps, phi 1, phi 2 and dot dot dot, T many endomorphisms of that. And I want to map it to a single representation of L2. Well, what vector space should I map it to? Anybody wants to give it a try? And today I did not request people to show their faces. And yeah, okay, maybe I can see only one apart from Anay. Yeah, anybody wants to try this out? That given a representation of LT, how we can obtain a representation of L2?
So L2 injects into LT, right? So we can see the restriction map.
Which restriction map?
L2 embeds into LT by identifying any two loops, any two fixed loops, and then drop other things. Right?
See. I think you came in late a bit. Yeah. So we have to preserve all the data. We don't want to lose information while doing this. Representation embedding means we have to preserve everything possible. So we shouldn't lose information. If you are saying that forget about 5, 3, 5, 5, 4 up to 5t, then that's not going to work. In fact, we have to design it in such a way that everything about 5, 1, 5, 2, 5t is already present on the right hand side.
B to the power t.
Correct. Like you are close, but yeah, the idea is actually v to the power t plus 1. Okay, so on one side, you literally take the t plus 1 size Jordan block with eigenvalue 0. So we are basically treating it as a sequence of morphisms. Yeah, one copy of VT is mapping to the second one is mapping to third one and fourth one and so on. So there is a chain. And for the other one, we actually duplicate the idea of the Jordan block. But what we do is this. So we have 0, 0, zeros on the diagonal, then 0 below, and then 5, 1, 5, 2, 5, 5t on the super diagonal. Okay, so yeah, it's a like once you know this, then it's a simple verification that it's functorial as well. Maybe I should show you what the functor is. I won't write down all the details, but if you have W with psi1, psi2, and so on, and this map is F, then this should be a T plus 1 cross T plus 1 matrix, which is again the diagonal one. Yeah, we are not doing anything else. You can again show that it is k-linear, it is exact, it preserves indecomposables. Okay, so all these things are true again. So now we know that the loop quiver problem is solved. In fact, I should tell you something very funny. Yeah, when I work with Anay, who is my PhD student, usually he draws some pictures and with some labels A and B for quivers, and then I ask him what is the underlying quiver, and he always says that just take the loop quiver. Yeah, he doesn't really care, and these steps actually show that loop quivers are sufficient. So that is our third thing. Yeah, the third point is that loop quivers are sufficient to solve the problem for any quiver. So step 3 is solve KLT. I mean for all t. Yeah, for all t, solve KLT implies for all q, solve KQ. Okay. So we are given some. So we have to start with rep K, KQ. Sorry, rep KQ. Yeah. And then we have to go until rep K LT for some T. But what is that T? Any guesses? Like an arbitrary quiver can have like finite number of vertices, finite number of arrows. Well, let me do it for you.
I don't understand the problem. Like, are you choosing a particular Q and then particular T, or
Q is given.
Q is given, okay. And
any
then
random Q is given, any random finite quiver is given, and you want to solve the problem for Q. But you want to show that if you have already solved it for all LTs, then you can solve the problem for Q.
So like you are giving this map from rep KQ to rep KLT, so that T is arbitrarily chosen, or you are choosing some T?
No, I'm asking what that T is, and I will give you the answer now.
Okay.
That it is basically take the number of vertices plus the number of arrows. Yeah, over here you can get this. So what is happening here? Well, a representation of Q, if you go back to the first lecture of Upendra, then it is just these bunch of vector spaces and a bunch of arrows, the linear maps, and you want to map it to this. Well, I don't think this is any hard to determine what the underlying vector space of this is going to be. It's just a big direct sum of Vi, where I varies over Q0. We have all the data in the vector space in the representation over here. And now there are how many loops? Well, as many vertices and as many arrows. So do you know the concept of, no, I don't think elementary matrices make sense. So what is this first thing? Yeah, so the first arrow corresponds to vertex 1, let's say. So vertex 1 means you are taking identity on V1 over here and then 0 everywhere else. Vertex 2, the second map corresponds to, well, let me try to write it as a block diagonal matrix. It is 0, then 1 V2, and then 0 everywhere else. And what happens to arrows? For arrows, if you have an arrow alpha, then you have added one loop for that. Yeah, so you have to encode the information over here, and it will be 0 everywhere except for one location. Yeah, where I'm calling it phi alpha, and everywhere else it is 0. Yeah, but this phi alpha location is the source alpha, comma, target alpha location in that matrix. That is the only non-zero block matrix, and everywhere else it is 0. And you do it for all the alphas. And then the natural diagonal map. So you can extend it to a morphism very easily. And hopefully you can see that we can solve the problem for Q, provided you have solved the problem for all LTs. Any questions?
In this block diagonal identity matrix, isn't it that redundant, or it's already intrinsically there? I don't still get the idea of adding Q not many loops.
But okay, so maybe I should write something more then. Yeah, if you are
And also,
confused about that, the map between representations is this. Yeah, it is indexed by the vertices. So how will you make sure that the vector space, appropriate vector space, goes to appropriate vector space under Fi? For that, you have introduced these block diagonal matrices with only one non-zero entry, because this is going to be a diagonal matrix F1, F2 up to F length Q0, size Q0. So the commutativity is being encoded in the form of that particular loop.
thanks.
Okay. Okay, so far we have only done it for all the path algebras of Quivers. And by the way, I'm not even considering finite dimensional here. Yeah, any path algebras of Quivers. Because even for infinite dimensional algebras like polynomial ring in 1 or 2 variables, you can have finite dimensional modules. Okay, so they are not our enemies at this point. And step 4 is, well, solve it for, like, for all Q, solve KQ. Implies for all Qi, solve KQ mod I. And this is just very simple, that representations of Q, K representations of Qi, that is simply a subcategory of the K representations of Q. Yeah, so if you have already solved the problem for that, then you have solved it for this as well. Nothing else to do. Any questions? Like, I have actually proved this statement that I set out to prove, that solving the classification problem for Kronecker quiver is sufficient to solve it for any finite dimensional algebra up to Morita equivalence.
Sir, in step 2, could you explain the Jordan block map, like the JT plus 1 comma 0 map?
Okay, sure. So maybe I should write it down. It's exactly the thing that I wrote on the other side. It is 0, 0, 0 on the diagonals, 0 here, and then 1, 1v1. Yeah, essentially 1v, 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 1v over here, and then again it is 0 at the top.
Oh, okay. All right, sir. Thank you.
Yeah. Okay.
Even here, can you tell me why we are taking the Jordan block instead of looking at the direct sum?
We want it to go from one place to another. Yeah, that's
okay.
V, the phi1, let's say phi1 on the left hand side, it goes from one copy of V to another copy of V on the right hand side. That's what we want to encode.
Yes.
Yeah, so yeah, nothing else.
But that is not the case in the left hand side, right? I mean,
it's not the case, but actually this is a representation embedding.
Okay.
That is sufficient.
Okay.
Okay. So all whiles are equally bad, if at all you are willing to accept that they are bad. Yeah, if you think they can, this problem can be solved, then please go ahead and do this. This will be great help to the community. But sorry, this is a mismatch of pages. Okay, so what is the actual definition, like a very technical definition of representation types that has been accepted for a long time? A K algebra is of Weil representation type if there is an A KXY bimodule. So here we are using the loop quiver L2 like this, such that as a right module, it is free and finitely generated. And this tensor functor is conservative. We are just asking for conservative property, which means it reflects isomorphisms and nothing more. These tensor functors with bimodules, except like barring this property, the conservative property, they are already representation embeddings. Okay, so this is sufficient because of these things. Of course, we have taken some conditions that it is free, finitely generated, etc. And I don't really want to get into details, and I don't want to scare you, but this is the commonly accepted technical definition of Weil representation type. On the other hand, yeah, so the tame representation type definition is this. Okay, a K algebra is of tame representation type if, yeah, so if we are talking about a finite dimensional algebra, then we want to classify all finite dimensional modules. So we just look at the variety of all the total dimension D modules. Yeah. Variety as in isomorphism classes. So except for finitely many isomorphism classes, which we can deal with separately, what happens is for any D, which is the dimension that we have fixed, total dimension, there are AKT bimodules. How many? Well, mu D many. We don't know what that is, what that number is. Mu D many bimodules, such that each mi is free of finite rank as a KT module. Okay, so same thing as above. If you notice here, I said mkxy is a free finitely generated right kxy module, and I'm doing like that. It was the loop favor 2, and here I'm taking loop favor L1. KT means KL1. So it is a free finite rank as a right KT module, and all but finitely many isomorphism classes. So I said leave out finitely many of A modules with total dimension D. They contain a module which is isomorphic to MI tensor a simple KT module. MI tensor a simple KT module. So all the simple KT modules, if you have done a basic course on commutative algebra, then you know what they are. They are simply KT mod T minus lambda for different values of lambda. And this lambda is basically the parameter that we are talking about. Yeah, one parameter family. So every MI gives you one parameter family. So there are many one parameter families, and except for that, there are only finitely many exceptions. So you still have a pretty good control over what all these things are. And just for technicality, I have written that A is not a finite representation type. We don't want to include finite representation types in tame representation type. That's all. Okay, so what we are saying here is that tame representation type means for any fixed total dimension, finitely many exceptional and finitely many one parameter families. That's the complete description. And then I think in the light of this new definitions, you can revisit the trichotomy theorem of Drost and Crowley-Bouvier, that every finite dimensional K algebra is of exactly one of the three representation types, namely finite, tame, or wild. You cannot have two representation, and you cannot have a fourth possibility. It's a very strong and very hard result to prove. The original paper, if I understand correctly, it's in Russian. It was written by Drost, so it's in Russian, but Crowley-Bouvier has written something afterwards. He gave some correction and a much better way of proving this. So I hope you can appreciate what the strength of this theorem is. Any questions? Okay. So then I want you to notice something. Yeah, you have started with a tame representation type algebra, and there is a symbol for every D. There is a mu D. So basically, we can treat this as a function from natural numbers to natural numbers. D mapping to mu D for a particular algebra that can be treated as a function. Okay. So tame representation type can be further classified into domestic or non-domestic. Yeah, zoology terminology. So what does this mean? This says that there is an absolute number such that mu D is less equal n for all D bigger equals 0. That is a domestic algebra, domestic representation type algebra, and non-domestic is literally it is not domestic. Yeah, there is no other definition over here. Okay, so you understand that you have one parameter families, but you can ask, as the dimension grows, how many new one parameter families are being added to the system? Is that growth polynomial? Is that growth bounded by something fixed? So polynomial growth function, algebras, people study them. Yeah, linear growth, polynomial growth, quadratic growth. Or you can have explosion. Yeah, the number is still finite, but it explodes. It can be exponential growth. So those all come under non-domestic side. So even within the tame representation type, people usually prefer to study the domestic representation types. I mean, it's easier to study them compared to the non-domestic ones. Any questions?
Yeah. So when you say a polynomial growth, you mean at each dimension, the number of irreducible representations grows as polynomial.
As polynomial in D. Yeah.
A polynomial in D. So that is
Polynomial in D.
also non-domestic, you mean.
Yeah, I mean, see, polynomial growth, the domestic ones can also be treated as polynomial growths, right? There is an absolute bound, but that thing obviously increases. What is the correct definition? There exists some number, let's say capital K, such that
here it
so
is constant, right? Here the
here it is
capital N.
absolutely constant, so it won't increase. But that also means it is linear growth, it is quadratic growth. So you have to ban this, that it is not a constant, it actually grows. Yeah, the sequence mu d, the function mu d is divergent. Its lim sup is infinity. Yeah, that you have to argue.
Okay.
Huh? Okay.
If it is polynomial, I still don't get it, but it's okay. I mean,
No,
if it's
polynomial
polynomial,
doesn't mean it's finite, right? This n doesn't depend on d in the definition of domestic. Yeah, polynomial means it can be 1, then 4, and 1, 4, 9, and so on. So it's not domestic.
And that, okay, that's not domestic. Yeah. Okay,
Yeah, that's not domestic. But I'm saying domestic can be thought of as polynomial growth, obviously.
Okay.
Yeah.
Okay.
Okay. So let us look at these two examples. And we'll look at more examples during the tutorial itself. But yeah, so Kronecker-Quiver K2. Yeah, this is same representation type. Then we would like to figure out what are all the indecomposables. I think I have shown you that there is something called a band and a band module. Well, if you are not present for the tutorial, I will just remind you what these things are. So there is an indecomposable presentation, representation of this kind for every lambda. Yeah, 1 and lambda. And if lambda is different, then it is not isomorphic to this. And then we saw in the tutorial that there is a chain. These are called tubes consisting of these things. But you don't even have to stop there. So I'm trying to do the first problem first. Yeah. So you can also take k to the n, then identity with size n. And over here, I can take the Jordan block with value lambda. So these are also indecomposable. And these are one parameter families. So basically, what are we saying? Yeah, where are we getting these one parameter families from? So from the so-called cyclic walks. Yeah, so each band provides a one parameter family. Okay, so what are the dimensions here of these family? Yeah, how many families are there really? In this case, the bands are cyclic strings. So the cyclic string I'm talking about. So the only bands here are alpha, beta inverse, and beta alpha inverse. Yeah, these are the only two bands. There are no other bands. So these are cyclic walks. So you put a copy of K at the beginning. Then for every arrow you traverse, either forward or backward, then you put a copy of K at the end. And once you have returned to the basic location, then you do not put a copy of K. Yeah, you complete the cycle. We did precisely that. And on any of the arrows, this is basically a cyclic walk. And on any of the arrows, you put a copy of lambda or a Jordan block of size lambda. Okay. So notice that the total dimensions of these band modules as this. So what is mu? Yeah, so this is D and this is mu D. For dimension 0, there is nothing. For dimension 1, there is nothing. For dimension 2, yeah, there is one band. I mean, these two are inverses of each other, so they don't really contribute anything different. So for dimension 2, there is one two-dimensional family. So that there is only one family. For dimension 3, again, there is no family. For dimension 4, there will be k square, k square. Yeah, so n is equal to 2 will work here. So again, one family. And dimension 5, 0. And this sequence will continue as 0, 1, 0, 1, 0, 1. So therefore, you can see that this Kronecker 2 quiver is of domestic representation type. I'm of course hiding behind all the theory that these are the only indecomposables and all the other string modules, so-called string modules, these are the exceptional ones, which do not lie in these one parameter families. And I'm not doing any proofs. But are you convinced that this is actually a constant thing? Yeah, this is domestic representation type. Whereas we try to play the same game on the other side with GP23. So GP23 is Gelfand Ponomarev, who you can say that they were the first people to talk about finite dimensional algebra's representation theory. Their paper in 1968. So these algebras are named after them. We kill some power of every loop. So we are killing a square and b cube, and then ab and ba also have to be blocked. So here there are bands. Yeah, so bands include. Can somebody please tell me at least one band over here? Something which is a cyclic string whose powers are defined. Cyclic walk, some cycle. Well, the workshop has become so hectic at the end of second week that nobody's willing to say anything. Okay, let me write that. The bands include A, B inverse, and more importantly, also this A, B inverse, B inverse. Yeah, so A, B inverse and A, B inverse, B inverse. These are two bands, but so are, yeah, look at this, A, B inverse and A, B inverse, B inverse to the power n. Okay, so the number of bands is infinite. So what you have to observe to check whether it is a band or not, is it the power of some smaller cycle? It's not, because I added AB inverse. Then the rest is a cycle power. But then I can also play the same game, yeah? AB inverse, M1 times, then AB inverse, B inverse, M2 times, and then AB inverse M3 times, and so on. And I can write down so many cycles. And as the dimension increases, then one new band will pop up, which has that length. And then it will continue contributing for all higher dimensions. Yeah, all its multiples. But the number of bands which pop up, you can't control that. There are infinitely many bands, and therefore their length is unbounded. The length of all the bands together is unbounded. So there will be new one parameter families popping up when dimensions increase. And therefore this is, yeah, so this was domestic, but this one is non-domestic. So all you have to check for is whether or not there are finitely many bands or infinitely many bands. In fact, that's the characterization. Yeah, the type of algebra I introduced in tutorial 4, the string algebra. So string algebras are domestic representation type if and only if they have finitely many bands. Any questions? Okay. The non-domestic ones, yeah, they are still not wild. Yeah, but working with them can be wild experience. So the non-domestic algebras have a certain feature which I alluded to yesterday at the very end. So I said that a module, well, let me talk about that for some time before I start with this. So say that a module M is super decomposable if it has no non-zero indecomposable direct summand. Okay, and who was there yesterday? Whose name starts with an R. Yeah, he mentioned that these will be infinite dimensional. Yeah, so Aditya, I'll come back to your question. Just hold on. So a module is super decomposable if it has no indecomposable direct summand. Can you think of an example which is super decomposable? Well, I'll give you one. Yeah. So let A be the endomorphism ring over complex numbers of complex vector space with infinite dimension. And let I be an ideal of A consisting of morphisms, maps with finite dimensional image. Then A mod I is super decomposable. Yeah, think about this example for a moment. Yeah, basically, if you have something which can provide you with finite dimensional things, you kill that part. So all the maps which have all the cosets of maps which have infinite dimensional image. Yeah, those are the things in those are the elements of this super decomposable module. So finding them is really hard. And if I remember correctly, then a module, an algebra is of domestic representation type, and an algebra doesn't have any super decomposable. Those two are equivalent statements, if I remember correctly. Okay. So, any questions about the concept of, yeah?
In some sense, that A should not be Artinian.
Huh?
A should not be Artinian. Otherwise, there will be a simple sum.
No. What should not be Artinian?
The A, the ring or the module would.
No. I don't think so. See, there are finite dimensional algebras, namely GP23 will have a super decomposable modules. Of course, in infinite dimensional. So whether the algebra is Artinian or not, that doesn't play any role.
Okay.
Non-domestic string algebras will have super decomposable modules.
Simple
And there is
modules are super decomposables, right?
Which modules?
Simples.
Simple as in infinite dimensional or finite dimensional?
Finite dimensional simple modules.
Finite dimensionals can't be indecomposable, right? Simples are indecomposable.
Yes.
So they have, I mean
direct
a
summand.
non-zero indecomposable direct summand, namely the simple itself.
Okay.
For finite dimensional ones, we have the Krull-Schmidt theorem, right?
Yes. That's
yes.
also. So
yes,
you cannot. Yeah. Okay.
I thought you excluded the trivial one.
Okay. So super decomposable modules are a special feature, and because I heard in the morning Ravindra was talking about Verma modules, and they are infinite dimensional modules. So I thought I should also talk about some infinite dimensional modules. Okay, so Aditya had some question here that how is this a cycle? Well, everything is a cycle here, Aditya. Yeah, but this only those cyclic walks, because there is only one vertex, so everything returns to itself. But only those walks are called bands if all their powers are defined. So for example, A is not a cycle because A square is blocked. B is not a cycle, A is not a cycle, AB is not a cycle because AB is blocked. But other things are cycles, and it is a band if all its powers are defined and it is not a power of something smaller. So it is a primitive walk. Hope you got your answer.
Yes.
Okay, thanks. Okay, so now what is the analog of super decomposable for morphisms? For morphisms, it is a factorizable system which was introduced by Prest. So what we have is simply some data of lots of modules. One module for each rational number between 0 and 1 endpoints included, with one specific point. So these are pointed modules indexed by rationals between 0 and 1, together with certain maps from from M alpha to M beta, where alpha is less than beta. So what they do, well, of course, they first of all, they have to form a composable system. So F alpha beta followed by F beta gamma is F alpha gamma. So basically, we just have one long morphism. Yeah, F01 is the long morphism, and we are talking about its transfinite factorization. And the base point should be mapped throughout to other base points under these maps. Well, these two are the simple things. The third property is the most important one, that none of these maps are invertible, even on one side. Yeah, so all these maps lie in the radical. They are non-split morphisms. Okay, so these are factorizable systems. And what can you do with them? Well, in this case, if there is a factorizable system, then what you can say that F01 or F alpha beta for alpha less than beta are maps in rad infinity. Yeah, the stable radical. So they can be factorized according to the definition of this thing. They can be factorized for every ordinal. They will continue to be in every radical power, every ordinal radical power. So these factorizable systems do exist in non-domestic algebras. Okay. So actually, like, I will come back to an example of this, but I want to talk a bit about what the stable radical says about representation types. So there is an old theorem of Auslander himself that a finite dimensional K algebra is a finite representation type if and only if rad to the power omega is 0. Okay. Then Prest and Schroer conjectured that a finite dimensional K algebra is of domestic representation type if and only if the stable radical, rad infinity, is trivial. Equivalently, rad to the power omega square is trivial. So basically nothing remains. There are no factorizable systems in domestic algebras. They actually proved this result for domestic string algebras, and then they conjectured it for all finite dimensional algebras. And recently, I have made a conjecture as well, which says that a finite dimensional algebra, K algebra A, is of tame representation type if and only if rad A infinity is actually rad A omega square. So it stabilizes before omega square. You don't have to go very far. And then it is expected that all the wild ones, they will sit at exactly at omega square. Yeah, but this is a very hard thing to do. And as I explained in the tutorial 2 days ago, that string algebras are good test candidates for various conjectures, testing various conjectures. So these conjectures have been tested on string algebras, and therefore we have made those claims. So the stable radical actually has a lot of control over the representation type. Anything to say? Any comments about this? Well, I have got 10 minutes and I have got two options to do. One is to explain a factorizable system, which I also intended to do in the tutorial, like explain it in detail. Or there was another thing which was about pure injective modules. But maybe I should stick to the thing that I have already introduced, because factorizable systems, I should show something to you. Okay. So I'm again talking about GP23 here, and the arrows are this, and you remember the relations a square b cube AB and BA. And then there is a module corresponding to this. So are you okay with me for writing B inverse? Module associated with B inverse is K, 0 and 1. I have only taken one identity map for one copy of B. Similarly, if I'm talking about module associated with AB inverse, it will be K. So how I'm constructing them, I will show over here. So this is B inverse. I put a copy here, then I put a copy here, and now there is A. So I put a copy of K here. So ultimately the representation, sorry, I made a mess here. It should be just K square. And then originally it was for A, the map is 0 and for the other one, it is 0, 0, 1, 0. If I'm not making mistake with left and right. Then over here, it is K cube. And you can observe the second copy maps to the third copy. So the numbering is 1, 2, 3, and the second copy maps to third copy. So I should put 0, 0, 0. Then at location 2, 3, or 3, 2. So third row and second column. So here I should put 1 and 0, 0. And this one is second copy maps to first copy. So which means 1, 2. 0, 1, 0, 0, 0, 0, 0, 0, 0. This is the map corresponding to B. So I introduced these things in earlier string modules. So what I'm saying, there is a map from B inverse to the simple module, which is just E1, which I can factor. Let me actually look at the factorization. Otherwise, it's not possible to write this down. And these are all string modules, so replace them by this. So B inverse, A, B inverse, B inverse, A, B inverse. Then over here, I have B inverse A, B inverse, B inverse A. Then over here, just B inverse AB, AB inverse, and B inverse A. So I have some inclusion here, then surjection here, then surjection here, surjection here, and surjection here. Okay, so what I'm asking you to observe is that the morphism which I have drawn here, maybe I should make these things red because they are spatial morphisms, red or green. So this is the spatial morphism I'm trying to factorize, and I want to show that there is a factorizable system associated with this. Okay. Yeah, I mean, you just have to believe me that this factors as a composition of these 5 maps. It's a hexagonal diagram, but notice something over here, which is so B inverse itself can be written as even B. Even B inverse is just this. So I'm going to underline certain parts. This part and this part. Similarly, observe that this part and this part. And observe, so I mean, let me make them double. And this, sorry, not this one, but this part and this part. So what is happening in every green morphism, I'm only adding a B inverse to the right. Which means if I get 2 green morphisms, then there will be another hexagon over here. There will be inclusion here, then a green map over here, a surjection here, then another surjection here, and a surjection here and a surjection here. Similarly, over here, there will be another inclusion followed by a surjection and a surjection, and there will be another green map here. So all these things, so in a factorization of one green map, I get two green maps. Then in the factorization of those individual green maps, I get two green maps. And in this way, I can obtain basically what we call dyadic rational numbers. So these factorizations are indexed by dyadic rational numbers, which, I mean, order theoretically, they are just same as rationals between 0 and 1. Okay, so this honeycomb-like structure will grow in all possible directions. And that gives us a factorizable system. And this factorizable system actually tells you that this map, the map from MB inverse, the string module for B inverse to the simple module at that vertex lies in the infinite radical, the stable radical. It keeps on factoring. Again, that morphism keeps on factoring. Yeah, this process doesn't ever stop. So this is the speciality of all non-domestic algebras. An algebra is of non-domestic representation type if and only if there is a factorizable system. All these things are, yeah, I mean, I find them really interesting. There is a lot of combinatorics. Like once you understand the algebraic results, then what remains is just combinatorics. And I have been working on this area for past 6 years now, 6 or 7 years, because I'm just fascinated with combinatorics. And I'm thankful to all of you for being with me until this very end, because this was my first time learning Auslander-Riemann theory and teaching it simultaneously. Okay, so I enjoyed the subject and I hope that you did too. And I will soon share a link with you for the feedback form. And I would honestly look for feedback on this subject as well. Yeah, subject as well as teaching. So whatever you want to convey, please do. And next week, remember that our lectures will start at 11. And Thomas Brussel, he is the speaker for next week. He was a PhD student of Gabriel. Yeah, and well, of course, Upendra was a student of Auslander at one point during his PhD. So we have got connections with big names. So Thomas will try to talk about certain topics which are not based on Auslander-Riemann theory. So even if you did not understand this part, he will talk about more recent developments in the field related to cluster algebras and other things. And they will be independent and won't assume a lot of background knowledge from what I covered. So thanks to all of you.